Good morning, everyone. And thank you so much for attending my defense. I'm Zhang, a PhD student for Zhang, supervised by Professor Luis Mohan and Yu Zhang. And the topic of my thesis is quality assessment of live field image. And currently, with the development of the immersive visual media, the traditional 2D images can no longer satisfy people's desires for immersive experience. And wherever in the world or in the entertainment, now there are more and more interesting immersive applications, such as augmented reality, the virtual reality, and the mixed reality. And to achieve the immersive experience, the live field image is one of the most widely used immersive media. An example of a live field image is shown here, and we can see that the live field image can record real 3D scenes from multiple viewpoints. And typically, live field image achieves immersive experience by recording the wavelength of light at any precision in the 3D space, and it is described by several parameter functions, in which the SY denotes the location in this 3D space, the lambda denotes the wavelength, T denotes the time, and the final two parameter denotes the horizontal and vertical angle of the input light. But in 1996, considering that this function is too difficult to be used in practice, so it is therefore simplified into a two-plane model, including an angular plane and a spatial plane. And this two-plane model also lays the foundations for most subsequent works related to live field. And for the live rate input to the end user applications, the live field image processing chunks can be roughly divided into 4 stages, including precision, representations, encoding, decoding, rendering, and display. And the first stage is the live field image acquisition. And currently, there are 4 methods to achieve this, including the multi-camera array, time sequential capture system, hypnotic camera, and computer graphics software. And generally speaking, the first 2 methods are the capture device in the early days, and the hypnotic camera and the computer graphics software are more commonly used at present. And secondly, according to different applications, we can obtain live field image in different representations. For example, if live field image is captured by the multi-camera array, then it will be represented in the aperture image array. And if the live field image is captured by the time sequential capture system, then it will be represented in the pseudo video sequence. And for the hypnotic camera, then it will be represented in the microcolor image. And moreover, we can get any kinds of the live field image representations with the use of the computer graphics software. And next, considering that live field image contains a lot of redundant information, the third stage is to encoding and decoding live field image so as to improve the storage and transmission. And generally, there are 2 methods for this stage, including the traditional coding tools and live field image coding methods. And then the final stage is to rendering and display live field image. Although the live field display is available now, its coverage is still very limited. So we still need to display live field image on a traditional 2D or 3D displays. And for now, the viewpoint shifting and recall focusing are 2 widely used rendering and display technologies on the traditional displays. And for the left figure, we can clearly see that the viewpoint shifting of the live field image. And for the right figure, maybe it is not really clear. Actually, the focus part of this image is changing from close to far and from far to close. And throughout the live field image processing chunk, different types of the distortions may be introduced in different states, which finally affects the visual experience of human eyes. And these distortions can be divided into 3 types, including super resolution related distortions and compression related distortions and other distortions. And here we provide a distortion example of the ghosting effect. But here we only show the central view for each live image. considering the space limitation. And for the right figure, we can clearly see that there exists a ghosting effect around the flowers. And here we should note that this example only reflects the visual effect in a single viewpoint, and the angular inconsistency will further affect the visual quality when switching between different viewpoints. And since these distortions may finally affect the visual quality of the image, how to benchmark or monitor the impact of these distortions is very important. And as a solution, the live field image quality assessment is proposed, which is the topic of our thesis. At first, the subjective experiments are conducted to evaluate the live field image quality by the human observers. But actually, this method is very time-consuming and expensive. So by collecting the subjective quality scores in the subjective experiments, the subject or the standard database is therefore built, and based on which the objective metrics can therefore propose. And compared to the subjective experiment, the objective metrics is more efficient and inexpensive. And according to whether the reference information is available, the objective metrics can be further divided into full reference, reduced reference, and no reference. And according to which kinds of the features, the objective metrics can be divided into handcraft feature-based and deep learning-based. However, the state-of-the-art method still has certain limitations, which motivate us to further investigate these research topics. And in the following, we will introduce the limitation of the state-of-the-art methods later. And here I summarize the contributions of our works according to their types. And specifically, we conduct a new subjective data experiment and database and propose several objective metrics, and including 2 no-reference handcraft feature-based metrics and 1 full-reference deep learning-based metrics and 3 no-reference deep learning-based metrics. And this results in 7 publications. However, limited by the time, in this defense, we only present 1 matrix from each type. And then we summarize the outlines of this presentation into a diagram. This presentation contains 4 parts. We first introduce the subjective experiments and benchmark in the part 1, and followed by the 3 metrics in the part 2. And then we would like to provide the experimental results in the part 3 and conclude this defense and this thesis and provide some perspectives in the last part. And first, we would like to start with the part 1 and introduce our subjective experiments and benchmark. Before building a new database, we first analyze the characteristics of the existing databases and briefly summarize their limitations. And here we can see that the existing database, they focus more on the distortion introduced by the traditional methods rather than those introduced by the deep learning methods. Second, we can also find that no existing database consider the multiply distortions. And then we can also find that existing database, they only focus on the real-world and dense synthesis live field images, but the sparse synthesis live field image have never been investigated. So motivated by these limitations, we aim to conduct a new subjective experiment and propose a new database focuses on the multiply distortions introduced by the deep learning-based methods. And then to build our database, we first choose 10 source sequences as the reference information, including 3 types of the live field image. And specifically, there are 4 real-world live field image and 3 dense synthesis live field image and 3 sparse synthesis live field images. And on the right side here, we provide the spatial information and colorfulness of our select SRCs. And we can clearly see that our select 10 SRCs has wide content diversity. And then we define 12 hypervertical reference circuits. Here, all the HRCs are generated from 4 basis methods, including 2 deep learning-based live field image angular reconstruction methods and 2 spatial super resolution methods. And they are denoted as A1, A2, S1, and S2 respectively. And based on these methods, we define 12 HRCs, including 4 individual distortions and 8 multiplied distortions. And note that in our database, the absorption order of these two different methods in the multiplied distortion is also considered. For example, using the A1 methods followed by the S1 methods and using the S1 methods followed by the A1 methods are considered as different distortions in our database. And in summary, we have 10 SRCs and 12 HRCs, so there are 120 distorted live field images in our database. And then we conduct subjective tests to collect the subjective opinions on the distorted live field image from 32 observers. And in the test, here we use the pairwise comparison protocol with the interactive viewpoint shifting to obtain the subjective opinions. And in this method, the observers will be provided 2 live field images, and they need to choose the one with better visual quality in their opinions. And then after obtaining the subjective opinions, then we can get the subjective scores. And that is each distorted live field image has 1 subjective score. And note that during the test, there is no time limitation for the observers. And second, we divide all the testing pairs into 3 parts according to 3 different types of the live field image. And finally, a 5-minute break is required after finish this part. And then after obtaining all the subjective quality scores for each image, we provide a quality score summary for each scene. And here, the figures on the top middle rows denotes the real-world stem synthesis and spot synthesis scenes respectively. And for the result, we can conclude that first, we can see that the same distortions may have different effects on different scenes. And then second, by comparing the top rows and other 2 rows, we can see that the real-world scenes tend to have better visual precision than the synthesis scenes when suffering from the distortion. And then by comparing the middle rows and the bottom rows, we can see that the visual effect of the dense synthesis scenes is generally better than that of the sparse synthesis scenes. And then we further provide the distribution of all the quality scores in our database. And we can see that the quality scores of the distorted live field images has a wide and reasonable distribution. And finally, we present the quality score distribution with respect to multiplied distortion introduced by 2 different methods. And here, different figures denote different combination of the angular reconstruction methods and spatial super resolution methods. And for example, for figure 8, the red bars denotes the quality score of using S1 distortions followed by the A1 distortions. And then the blue bar denotes the quality score of using A1 distortions followed by the S1 distortions. So these results focus on investigate the differences between these 2 multiplied distortions. And for all the figures, we can clearly see that most red bars are taller than the blue bars. That is, using a spatial super resolution method followed by an angular reconstruction method generally obtains better visual effects than using the reverse order. And then we provide a benchmark of the overall framework, overall performance comparison of the existing objective metrics on our database. And our proposed database is named IETR live field image. And also, we provide the performance on 2 individual distortion databases. And in this benchmark, for example, we can see that although the matrix proposed by Zhang in 2023 has good performance on 2 individual distortion databases, but actually it doesn't perform well on our database. This indicates that its performance on the multiple distortions is limited. As a result, we can draw the conclusion that this benchmark can reveal the limitations of the objective matrix on multiple distortions introduced by the deep learning-based methods. Well, to make a conclusion in the part 1, we propose a new database and focuses on the multiple distortions introduced by the deep learning methods. And then we also build a benchmark of the existing objective matrix on our database. And then in the next part, we will introduce our proposed objective matrix in more detail. Then in the part 2, we first introduce the handcraft feature-based matrix named SATV3. Here, we first provide a general framework for the state-of-the-art handcraft feature-based live-to-image quality assessment matrix. And for the full reference matrix, we can see that both distorted live-to-image and reference live-to-image are converted into the different representations, and then followed by the feature adjustments and pooling methods to predict the quality of the live-to-image. That's the general framework. And then for the reduced reference matrix, the reference information is no longer available, but instead there are other forms of the information from the reference information, such as the balance map, deep map, and all-in-focus map. And for the no reference framework, only the distorted information is provided in this framework. And among these 3 types of the matrix, the no reference matrix are more suitable for the practical applications, but it is also more difficult to be developed. And so in this business, and we therefore focus more on the no reference matrix. We then go deeper into the state-of-the-art no reference framework. We can see that there are many kinds of the representations and many kinds of the features that have been used in the state-of-the-art no reference matrix. For example, the PVRI matrix proposed by Zhang in 2021, they use 3 kinds of the representations and 4 kinds of the features to predict the quality of live-to-image. And further, we summarize the representations and features that used in the state-of-the-art no reference matrix. We can clearly see that most existing matrices, they use multiplied representations and multiplied features for quality assessment. And this often results in very high computational complexity. And they often use about 100 seconds to predict the quality of a single live-to-image. And also, they are impossible to be applied in the real-time system. So we argue that they use multiplied representations and features is to ensure a competitive performance of quality evaluation. And this also indicates that their individual features are not efficient enough for the quality evaluation. So this also motivates us to develop an efficient matrix that with very low time complexity. Our proposed matrix also follows the general framework of the no reference matrix, but we only use the textual features to make sure that our matrix has very low complexity and efficient image textual descriptor is required in our matrix. And here we adopt the local binary patterns, the LBP descriptor, because it can extract the quality aware features, the quality aware textual features with very low computational complexity. And specifically, for a pixel in an image, we compare the value of each pixel, the central pixel and its neighboring pixel. For example, if the central pixel is larger than the right pixel, then the right position will be set to 0, otherwise 1. And then we can get a binary numbers, and then we connect all this A binary number into a bit binary numbers. And as a result, each group of the binary number is considered as one pattern, and then we can obtain 256 patterns in total. However, considering that the large pattern number will result in the lack of the rootedness, then we propose the LBP. We use the LBP with rotation invariant uniform patterns to reduce the pattern numbers. So in this case, this version of the LBP only contains 10 patterns. However, LBP is the tetra operator for the traditional 2D images. How can we adopt this LBP on a live image with the spatial and angular information? That's the question. So for the spatial domains, we directly apply the LBP on each spatial pixels in a wheel, and then we can get the spatial textual matrix with 10 patterns. And then we extend this operation to the angular domains. For each pixel in a single wheel, we consider the same pixel of the neighboring wheels as the neighboring pixel in the angular domain. So in this way, we can also get the angular textual matrix with 10 patterns. So based on this LBP, we decide a novel framework to evaluate the live image quality. So first, given a distorted live image, we first convert it into grayscale, the distorted live image, and then we adopt the LBP on the angular and spatial domains, respectively, and then generate the spatial and angular textual matrix. And then we merge these two matrices into a uniform matrix that containing 100 patterns. And finally, we calculate the histogram for all the patterns as the final features and predict the quality score using the support vector regression. Well, that's all about the first matrix. And in this session, we propose a new no reference matrix based on the spatial angular textual features. And this matrix has very low complexity, but achieves competitive performance of the quality evaluation. And we will provide the experimental results later. And in the next session, we will focus on the deep learning-based live image quality assessment metric. And our second metric is named EDVMF. Considering that the deep learning technology has adopted in many fields and achieves the impressive performance, so we would like to explore the deep learning technology into live image quality assessment. And currently, there are only a few live image quality assessment metrics that using deep learning features. And we also summarize the general framework for them, and which contains two highlights. For the first highlight, generally, they train the deep models using the data augmentation and directly predict extract the deep features from the whole live image and to predict the quality, to predict their quality. And this pipeline usually has very high computational complexity, and also it is very difficult to train a deep model despite using the data augmentation. And second, the second pilots no longer take the whole live image as the input. Instead, they divide the live image into a large number of 2D representations, and then they extract the deep features from these 2D representations for quality assessment. However, this pilot also have some questions. It is very difficult to define the quality aware representations, and it is also difficult to extract effective features from them. So due to these difficulties, the performance of the existing deep learning-based metrics still has a lot of room for improvement. So this also motivates us to propose a novel, efficient, but an effective deep learning-based metric. And our proposed framework also follows the second pilot. And based on this pilot, we have two difficulties to deal with. First, what kinds of the representations can reflect the live image quality? Second, how to extract the quality-aware features from these representations. That's too difficulties for us. And in addition, we also know that currently all the existing deep learning-based metrics are all no reference. And considering that the reference information may be available in some cases, so in this there is a blank in the full reference matrix for deep learning-based live image quality assessment. So this motivates us to fill this gap. Here we present the overall framework of our proposed EDDMF metric. Generally, given a distorted live image and its reference information, we first propose a patch generation model to extract both the spatial angular patches and sub-aperture patches. That is to address the first difficulties. And then these two kinds of the patches are then input into two different modules to extract the angular features and spatial features respectively. That is to address the second difficulty. And then finally, all the feature after all the feature extractions and in both streams, we directly concat these two features and predict the patch quality using the fully connected layer. To address the first difficulties, considering that the live image contains both angular and spatial information, our key idea is that the 2D representation should reflect both angular and spatial information. So in this model, we first extract the white components of the central 5x5, central A by A views of the live image, and that is to reduce the computational complexity. And here A is set to 5 in our metric, and then we define A by A sliding windows to lie over the live image and directly state the small patches into the aperture patch. And then we reshuffle the pixels in the sub-aperture patch into the spatial angular patch. As a result, we can generate a large number of the spatial angular patches and sub-aperture patches from one live image. And among them, the spatial angular patch is for the angular features, and the sub-aperture patch is for the spatial features. And after generating the patches, a pair of the spatial angular patches, including the reference one and the distorted ones, is then input to the hierarchical discrepancy network to measure the angular information. The hierarchical discrepancy network is shown here. This hierarchical design is motivated by two observations. First, different types and different levels of the distortions may lead to different effects in the angular information. And second, the shadow CNS layers extract the angular information, but actually, as the network deepens and the feature mesh size decrease, it tends to focus more on the spatial angular information. Therefore, we propose this hierarchical design to extract the spatial angular features with different angular encoding levels. And then after extracting the features from all the levels, then all the features are concatenated and then followed by the fully connected layer to predict the to generate the hierarchical discrepancy features. And then a pair of the aperture patches, also including the reference one and the distorted one, is then input to the local discrepancy extraction model to measure the spatial information. Here, to extract the spatial features, we propose this simple but efficient module. The motivation is that we observe that the traditional full reference 2D image quality assessment metrics can already capture the spatial distortions when the reference information is available. So we propose to compare the STEM local regions between the distorted information and the reference information with a full reference 2D metric. And here we use the very classical SIMS metrics in our framework. And after obtaining the quality score for all the matches, for all the regions, then we directly combine all the scores as the local discrepancy features to measure the spatial information. And finally, after generating the quality of all the patches, then we use the average pooling to obtain the overall quality of the live field image. So in this session, we propose a new patch-based full reference matrix using deep learning features. And as it will be seen in the next part, the proposed matrix achieves excellent quality evaluation performance. And this also demonstrates the potential of the deep learning technology in the live field image quality assessment. And however, considering that the reference information is not always available, we will go into a deep learning-based no-reference matrix in the next session. Our third matrix is named PV blade. The motivation of the PV blade matrix starts from the potential is in our previous EDDMF matrix. That is, it is unclear whether the live image quality is well inherited by the 2D representations. And based on these issues, we summarize the representations that used in the subjective experiments. And we find that actually the pseudo video sequence, the PVS, is commonly used to visualize live image in the subjective test. So motivated by this, why not we use the 3D representations, the PVS for quality assessment? And as a result, and here the PVS is generated by the arranging each view of the live image as a frame, and then displaying all the views in a certain orders. And then we spatially divide the PVS into a large number of 3D plots, and that is to ensure enough training samples to train a deep model. And here, each 3D plot is therefore then the pseudo video plot sequence. That is the PVBS. And then another potential issues in the EDD environment is that the use of the average pooling to combine all the patch quality into an overall quality. Actually, it is of course not an optimal solution. So considering that different regions may have different contribution to the overall quality of the live image, we propose to pool their quality to based on their importances regarding to the overall quality. First, we argue that the importances of each regions can be reflected by its balance value. And here we will not go deeper into this because many researchers dormitory is fatness. And in addition, we find that the PVBS variance is related to the predictive accuracy. That's very interesting. Here we show the relationship here, and we can see that the the PVBS with low variance, their predictive accuracy actually is not very stable. So in this matrix, we propose to discard this low variance PVBS to obtain better pooling quality. And then here is the overall framework of the proposed PV blade metric. And here, given a distorted live image, we first convert it into a large number of PVBS for quality assessment. And then, based on this PVBS, we propose a CNN-based PVBS net to extract the spatial angular features and then evaluate the PVBS quality. And finally, a balance and variance guide pooling, the SV pooling method is proposed to obtain an overall live image quality. And in the following, we will go deeper into the second and third normative. For the PVBS net, we divide it into 4 stages according to different functions. The first stage is the multi-information division. And this stage is the key of our proposed network because we can see that the angular information actually is scrambled after converting the live field image into PVBS. So, but we still find that actually there is a certain patterns in this arrangement. So we propose to reconstruct the horizontal and vertical information with different 3D CNNs. That is the first stage. And then the second stage is to extract the horizontal, the spatial horizontal features and spatial vertical features with the 2D CNNs. Actually, this stage aims to just to get deeper features. And next, the third stage establish the relationship between these spatial angular features using the GRUs. And this stage is to build the features from different rows and different clouds. And finally, in the final stage, we use the fully connected layer to predict the quality of each patch. And then for the SV pooling, it also contains two components, including the salience and variance. And first, we calculate the maximum salience value of the PVBS as its weight. Here, we use the maximum salience value because that is based on the consideration that the human eyes pay more attention to certain regions, often because there are some notable points in it. And then we define the high variance PVBS based on the variance ranking. Here, we first rank PVBS according to their variance, and then we use half of the PVBS with higher variance as the high variance PVBS. And finally, we rate the importances of each PVBS and obtain the overall quality using these two components. And in conclusion, in this session, we propose a new deep learning-based no reference matrix based on the 3D PVBS. And currently, this matrix is one of the best performing matrices to predict the live field image quality. And experimental results will be provided in the next part. So we would like to provide experimental results to demonstrate the effectiveness. Our experiments are performed on 6 different live field image quality assessment databases, including our proposed database. And here we summarize the main characteristic of each database, and we can find that they have different focus and different characteristics, and based on which we can conduct more reliable experiments. And in addition, we use the Lift2 Pro outcomes validation to report the performance, and the standard evaluation criteria, PLCC, SRCC, RMSE are used to report the performance, and this focus on different predictive results, different aspect of the predictive result. And here we report the overall framework on 6 databases, and we can see that the performance of the proposed matrix is compared with a large number of state-of-the-art matrices. The top row denotes the database. The first column denotes the matrix type. The second column denotes the matrix name. And the middle columns and the final column denotes the performance and time complexity for each metric. And in this table, these 6 rows are the results of the proposed matrix. And the best, second best, and third best results are marked in the broad, blue, and underline. And the red stars denotes the deep learning-based matrix. And for this brief table, we can easily see that our proposed matrix have more best 3 results. But actually, it is not very clear to directly show the performance of our proposed matches. So for better visualization, we summarize this big table into a trade-off figure between the time complexity and the performance on the Win5 database. Like this. This figure is shown here in this figure. The X direction denotes the time complexity. The Y direction denotes the SRCC performance on the Win5 database. And our proposed matches are marked with the blue symbols. The reduced reference matches are marked with the yellow symbols. The full reference matches are marked with the green symbol, and the no reference matches are marked with the purple symbol. And we can clearly see that our matches are in the top left corners, indicates that our matches have lower time complexity and better performance. And also, with the use of the leaf true false cross validation, we actually conducted experiments with different trend test speeds and often different results. So we provide a false pro of the SRCC distribution on the Win5 database. And in this figure, each box denotes the SRCC distribution of one metric. And the higher box position denotes better predictive accuracy, and smaller box length denotes better stability. And as shown in the figure, we can clearly see that the box our proposed metric is very small and at a high precision, indicating that our matrix has excellent stability. And to further evaluate the predictive accuracy, we provide a scatter plot of the subjective score and against the objective prediction on the Win5 database. And in this figure, the better fit between the scatter plots and the red line indicate the better predictive accuracy. And we can also see that our matrix has very good predictive accuracy. So in the final part, we conclude our words and provide some perspective. In summary, we have two main contributions in this in the research of live image quality segment. First, we propose a new database and provide some analyzed results and a benchmark of the existing objective metric. Second, we propose two handcraft feature-based metrics and 4 deep learning-based metrics, and we test them on 6 publicly available databases. And then I would like to provide some perspective in my future work. And first, as we mentioned before, the viewpoint shifting and the refocusing are two widely used methods to present live field image on the traditional display to observers. In fact, actually, we argue that the subjective scores obtained in this way actually may not be able to fully reflect the characteristic of the human eyes, because actually the live field image they are not present in their original 4D representations. Although all the existing subjective experiments use this way. So based on this consideration, our first perspective is that we would like to collect the subjective scores on the observer on a live field display. So to achieve this, I have found some live field displays available on the commercial market, but actually they are currently a little bit expensive. And we are looking forward to investigate this research topic as long as we have enough funding. And generally, the first perspective is that generally we train the objective metrics on an individual database, and the performance evaluated on this way is they often indicate a good performance, but actually we will get very bad performance if we train the metrics on one database and testing on another database. So our second perspective is that maybe we can let the metric to learn the differences between these two databases, and so that we can get better performance even when trained on other databases. And this research topic is named domain adaptation for the live image quality system. That's the second perspective. And further, here we summarize the general framework of the existing objective matching. In the training state, the objective matches generally extract the features for distorted live image and then use the SVR to map the features to the subjective qualities to build a mapping model. And then in the test stage, we only get the distorted live image, and then we extract the features, use the same weight, and then we use the trained model to map the features to a predicted quality scale. That's the general framework. But actually, this matrix is to measure how close the distorted live image for testing is to the distorted live image with the subjective score for training. That is to measure how close they are. And actually, the application of these methods highly depends on the size and accuracy of the subjective scores in the training set. So considering that actually we can easily get the reference live image now, our third perspective is that maybe we can develop an unsupervised live image quality assessment matches. So in this matches, what we need to measure is to measure how far is the distorted live image for testing is to the reference live image for training. That's quite different. I got this motivation from this literature. Well, that's all. Thanks for attention. And any questions are welcome.